to logarithms. Just the basic rhythms we'll use in chemistry. So a logarithm is a way of dealing with exponents. So if we wanted to solve for y in this equation, we could use a logarithm. So the logarithm sets it up so that we can solve for y, or the exponent. So 10 to the 4 equals x is the same thing as y equals log base 10 of x. So y is the power that 10 must be raised to get x. Y is the power that 10 must be raised to get x. So we can think of a logarithm in this way. Y equals log base 10 of x is read as y is the power that 10 must be raised to get x. Y is the power 10 must be raised to get x. Now, the number down here is the base, and it corresponds to this number. Often that number is not written, so when this is written, y equals log of x, the 10 is understood to be there. So this is understood to be base 10 unless it's stated otherwise. Let's try a few examples with logarithms. So first let's look at solving logarithms without a calculator. So if we have the question 8 equals log of x, now although it's not written, this is understood to be a base 10 logarithm since nothing is there. So we can interpret this or understand this as 8 is the power that 10 must be raised to get x. 8 is the power that 10 must be raised to get x. So we could write that like this. 8 is the power 10 must be raised to x. So x is 10 to the 8th power, and we'll just leave it as that. Y, let's try another problem. Y equals log of 0.0010. Now numbers like this are the types of numbers that we see in chemistry, these decimal numbers. So first I'm going to simplify that number there, 0.0010. I'm going to write this in scientific notation. So this would be 1.0 times 10 to the 1, 2, 3 negative third power. So we could express this as y equals log of 1.0 times 10 to the negative third. Now remember that this is a base 10 logarithm, so that's understood to be there. So we could write this. Also, we can simplify this even further. Now, since there's a 1 right here, does the 1 do anything? No, the 1 doesn't really do anything. It doesn't change the number, so I'm just going to ignore that 1, and I'm going to think of it like this. Y equals log base 10 of 10 to the negative third. Now, y is the power that 10 must be raised to get 10 to the negative third. So if we write it now in that form, y is the power that 10 must be raised to get 10 to the negative third. Now we have bases that are the same, 10 and the 10 cross out, and we're left with equals negative 3. Notice here, so when we look at this problem, negative 3 that was way back here. So notice that if we have a base 10 logarithm and this coefficient number in scientific notation is simply a 1, so that there's a 10 here and a 10 right there, those will end up dropping out. And so the answer comes out to be the exponent. So for many of our problems and to estimate a lot of the pH problems, we can use this idea right here as a good estimation to solve pH. But let's first take a quick look at using a calculator for situations that don't come out quite so neat and easily. So logarithms with a calculator. So if we have a calculator, scientific calculator, let's try this. Log y equals log of 7.56. So in this calculator, I would type in 7.56 and log, and there we go. This is the base 10 logarithm. Careful that you don't use natural log, so that would be ln. So we have 0.87, let's see, so y then is 0.88. Okay, so then next we have this problem. Y equals the negative log of 4, 5, 6. So again, use your calculator. So in this calculator, I would type 456 log, and then I would put the negative key afterwards. So I get 2, negative 2, negative 2.66. Let's try this other style of calculator. So in this style of calculator, if I did the first problem, I would do the log function first, then I would do 7.56 close parentheses equals, and in this second problem, I again would put the negative key, then log, then 456 close parentheses, should get the same number. Good. What about scientific notation? We have something like this. Y equals log of 1.4 times 10 to the negative 6. 1.48 times 10 to the negative 6. So in this calculator, I do 1.48 e, 6 negative, and then I press log. So negative 5.83. Now, in the other style of calculator, so I would do log 1.48 second e negative 6, close parentheses, equals, and it looks like we got the same answer there. Okay. What if we were going the other direction, anti-log problems? Let's take a look at how we do that in a calculator. So if we have 2.56 equals log of x, and we want to know what x is, we can use the anti-log key. 2.56 second 10 to the x, and that solves the problem. There should be an equal sign. So again, what we did basically is we changed the form of this, since that's log base 10 of x. 2.56, the power that 10 be raised to get x. So we use this button here, 10 to the 2.56 power. 2.56 second x, and so x comes out to be 363. In this style of calculator, it would be second and log, let's see, where is that? So we have 10 to the 2.56 close parentheses equals, get the same answer. Alright, let's look at some simple applications of the pH concept. Now, pH is a measurement based on the reactions of acids and bases with water. When water, even pure, water will react with itself to form some hydronium and some hydroxide. So one water molecule acts as an acid, donating its H plus to the other. This one's a base, that's the acid, producing hydronium and hydroxide. Now this is the basis by which pH. As those levels change, pH can be determined. In a neutral solution, the hydronium concentration is equal to the hydroxide concentration, and both of those are equal to 1.0 times 10 to the negative 7. And this is at 25 degrees Celsius. So, although that's a very small concentration, it is measurable. Now, for a neutral solution of pure water, the hydronium and hydroxide concentrations are the same. But when something is more acidic, the hydronium is higher than the hydroxide, and if it's basic, the hydronium is less than the hydroxide. And so neutral, again, the concentration be at 10 to the negative 7. Now, chemists think of this in terms of concentration of these ions. But to make this more clear, the pH concept makes this number of in concentration more simple. You see, this results in concentration of values like this: 10 to the negative 1, 10 to the negative 2 molar, 10 to the negative 3 molar, 10 to the negative 4, 10 to the negative 5, 10 to the negative 6, and so on. Now the pH concept translates that into a simple number like this: 1, 2, 3, 4, 5, 6, and so on. So here's the concentration in molarity in each value. So the formula that allows us to translate this to that uses this idea of logarithms. The pH is the negative log of the hydronium concentration. This allows us to convert the exponent to the pH value. Let's take a look at an example. So what if we had, for instance, an hydronium concentration So what if our hydronium concentration, H3O plus, is 1.0 times 10 to the negative 12 molar. If we want to know the pH from that, we can use this formula that we just wrote down. The pH is the negative log of the hydronium concentration. So the hydronium concentration is up there. We'll plug that into our formula. Brackets, by the way, mean concentration and molarity. Now, if we continue to solve this, for one thing, this is a base 10 logarithm, so we can put that 10 in there. And I also need to move the negative sign over here before I solve this, so I'm multiplying both sides by -1 to do that. So we have this expression: the negative pH is the log base 10 of 1.0 times 10 to the negative. Now, we saw earlier that the 1 can be ignored. So we have this expression: negative pH is the log base 10 of 10 to the negative 12. That 1 doesn't do anything, we're just multiplying by 1. So this looks familiar. The negative pH is the power that 10 must be raised to get 10 to the negative 12. The negative pH is the power that 10 must be raised to get 10 to the negative 12. The bases drop out, and the negative pH is equal to negative 12. Multiply both sides by -1. The pH is 12. Well, there's a shortcut. This number came from right here. Well, it's just like these problems that this problem we saw earlier. Just like we saw before, we can take this number, the answer, given that the coefficient is 1 and it's a base 10 logarithm, that matches the exponent above the 10. In the same way, this matches that exponent. The difference is, however, there's a negative sign in the formula which changes the sign so that we no longer have a negative exponent, it's now positive. So the sign gets changed. This is what allows us to have such a simple system for pH. The negative number on the molarity values becomes a simple positive number for pH. Now, larger concentrations, as a result, have smaller pH numbers. You see, the less negative this is as we go up, that means it's a larger concentration, and so it has a smaller pH value. So we notice then that acidic solutions are less than 7 when the solution is right at 7, 10 to the negative 7th. The pH is 7, so this is neutral. And then as we go to basic solutions, 10 to the negative 8th, 10 to the negative 9th, 10 to the negative 10th, 10 to the negative 11th, 10 to the negative 12th. pH is 8, 9, 10, 11, 12, 10 to the negative 13, 10 to the negative 14, 13, and 14. So these solutions then have a smaller concentration of H3O plus, like this. The negative numbers are getting further and further, more and more negative, further from 0. Looks like this picture. And so basic solutions have larger pH values. Now we can change up these problems a little bit as well. So maybe we might do a problem like this. If the pH is 6, what is the hydronium concentration? So in this case, we're just working in reverse. We know that the pH is the negative of the hydronium ion concentration. Well, we can move this around. We can plug in our base, which is 10, move that negative over here. So we now have this expression: the negative pH is the log base 10 of the H3O plus concentration. Now if we change this to exponential form, the negative pH is the power that 10 must be raised to get the H3O plus concentration. So the negative pH is the power that 10 must be raised to get H3O plus concentration. So the pH is 6, so 10 to the negative 6 is the H3O plus concentration. Now technically, since brackets mean concentration, we should insert the unit capital M for molarity in that problem. Let's try one other situation that occurs. There's another value similar to pH called pOH. Now, since hydronium ion concentration increases, the OH decreases, or vice versa. As one gets bigger, the other gets smaller. So a pH of 1 and a concentration of 10 to the negative 1 molar, that would, for the OH concentration, be 10 to the negative 13. So OH concentration then is 10 to the negative 13th, 10 to the negative 12, 10 to the negative 11, 10 to the negative 10, and so on. And if we do the same process and find the pOH, we end up the pOH values 13, 12, 11, 10, in a similar way that we found the pH. So the pOH is found by taking the negative log of the hydroxide ion concentration. So the pOH is the negative log of the hydroxide ion concentration. So we can use this idea to solve situations. For instance, since as the pH goes up, the pOH goes down, we'll notice that the pH plus always add up to 14. Let's try this example. What is the pH of a solution if the OH concentration is 1.0 times 10 to the negative 11th? So since we have the OH concentration here of 10 to the negative 11th, we can use the same shortcut. The pOH then, since it's the negative log of the hydroxide ion concentration, this is a 1 and we have a 10 raised to a power of negative 11. We can simply OH then is this exponent made positive. pOH is 11. Now, we just wrote an expression over here that pH plus pOH is 14. We know the pOH. The problem asks for the pH. Now it's just a simple matter of subtraction. pH plus 11 equals 14. Or in other words, the pH is 14 minus 11, or the pH is 3. So although pH seems complicated on the surface, much of it can be very simple, and much of it can be estimated by looking at these exponents. When we are going from pH to the concentration, we just take that number and write it as a negative exponent of the concentration. Likewise, when we go from a concentration value to pH, the exponent, change the sign, becomes the pH. And then when we're switching between pOH and pH, it's simply a matter of subtracting from 14 to get those answers.